Hi everyone, I am Dr. M. Janakarani, working as professor in the Department of Electronics and Communication Engineering. Today we will discuss about the design of synchronous counters. So first of all, what is a counter? A counter is a sequential logic circuit which is used to count the number of clock pulses that are arriving at its clock input. Basically there are two types of counters. One is synchronous counter, another one is asynchronous counter. Asynchronous counter has more delay when compared with the synchronous counter. So for high speed operations, in most of our applications, we use what is called as a synchronous counter. Suppose if you take a counter, it can be designed using what are called as flip-flops. And if you say a n-bit counter, a n-bit binary counter has 2 power n output stage. For example, if I say a 3-bit counter, it can count from 0, 0, 0, 0, 0, 1 up to 1, 1, 1. So there are 8 output stages in a 3-bit counter. Suppose if it is a 4-bit counter, it can count up to 16 states. Then the next one is a mod n counter or modulus n counter. So in a modulus n counter, it has only n output states. The remaining states are not used in the application. That is what is called as a modulus n counter. Then coming to the applications of counter, the digital counters are mainly used in digital clocks and watches. They are also used in interstates for digital event counting, and it is also used as a digital timer. And in digital communications, for providing the timings, we use this counters and also to count the number of clock pulses. So it is a very important digital logic circuit which has wide applications. The next one is how to design a synchronous counter. So the design of synchronous counter involves 5 steps. First one is we have to determine the number of flip-flops which are required to design a counter. Second step is we have to choose the type of flip-flop. The third one is we have to determine the excitation table of a counter. So we know that excitation table gives our flip-flop inputs for the particular present state and the next state. So if you know the present state and the next state, then using the excitation table, you can find out the flip-flop input functions. That is the third step. Then the fourth one is we want to get the input for the flip-flops. That is done using what is called as a K-map. So if we are using K-map, we can derive the flip-flop input function. The last step is using the Boolean equations for the flip-flop inputs. We can draw the logic diagram for the counter. Now we will see one example. The problem is design and implement a mod 5 counter using JK flip-flops. We will see how to do the design and implementation. So the first step in the solution is first we have to find out the number of flip-flops that are required for implementing the counter. So here we have to make use of this condition. 2 power small n should be greater than or equal to capital N, where n is the number of flip-flops required and capital N is the number of states in the counter. So in our problem, the number of states is given as 5. Mod 5 counter means we should have 5 stable output states produced by the counter. So the number of states here is n, capital N is equal to 5. Therefore, 2 power 3 is actually greater than or equal to 5. Hence, the number of flip-flops needed to implement this counter is 3. So that is the first thing. Second point is the type of flip-flop should be determined. In the problem itself, they have given we have to design it using a JK flip-flop. So the type of flip-flop is JK, and this is a symbol for a JK flip-flop. And here J and K are your inputs, Q and Q bar are your outputs. So like this, I need 3 JK flip-flops to implement the required counter. So first we should know the excitation table of the JK flip-flop. So this is the excitation table of the JK flip-flop. The excitation table gives the flip-flop input functions for the present and the, if we know the present state and the next state of a circuit. So here in this one, Qn is the present state, Qn next state. J and K are the inputs to this flip-flop. So if I want to have the J and K inputs for the present state 0 and the next state 0, my J input should be 0 and the K input should be X. Similarly, for the present and the next state 0, 1, JK inputs are 1, don't care. It is not X, it is a don't care in digital. Then for 1, 0, it is don't care 1. For 1, 1, it is don't care 0. So now we know the excitation table of the JK flip-flop. With this, we will go to the next one, that is the excitation table of the mod 5 counter. So for the counter, first we should write the present state, then the next state, then the flip-flop input. That is what is called the excitation table of the mod 5 counter. So here this is actually having 3 flip-flops. So like this, we are having 3 JK flip-flops are required in our counter design. Flip-flop 1, flip-flop 2 and flip-flop 3. So here the inputs here are JA and KA. Here the inputs are JB and KB. Here the inputs are JC and KC. And the output here is QA. Here it is QA bar. The output here is QB and QB bar. Here it is QC and QC bar. So our aim is we want to find out what are the inputs to the JK, 3 JK flip-flop, JA, KA, JB, KB, JC, KC. For this one only we are writing this excitation table as per our design constraint. So here it is a mod 5 counter. So it is a mod 5 counter. So it counts from 0 to 4 and after that it resets to 0. So the count sequences here are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, then 1, 0, 0 and after that the counter should reset to 0, 0, 0. So this is the sequence. Mod 5 count sequence should be like this. So if my present state is 0, 0, 0, my next state is 0, 0, 1. That is what I have written under the next state 0, 0, 1. Suppose the present state is 0, 0, 1, the next state is 0, 1, 0. Present state is 0, 1, 0, the next state is 0, 1, 1. The present state is 0, 1, 1, the next state is 1, 0, 0. If the present state is 1, 0, 0, this is the important step here. If the present state is 1, 0, 0, the next state should be equal to 0, 0, 0 as I showed in the count sequence. So first we have written this one. This is the required count sequence. Then for the it is a 3-bit counter. So in a 3-bit counter we know that 2 power 3 that is 8 states will be there. So this you know already. This is 0, 1, 2, 3, 4. This one is 5, 6 and 7. So these 3 are not required in our design. So we can mark the outputs, the next state as all don't care. Similarly the flip-flops outputs, inputs are also equal to don't care. So this we can finish it off first. So the next thing is we have to find out the flip-flop inputs. So for this one first I have written JC then KC. So if the present state is 0, the next state is 0, the input should be 0x. So you can see here this is QC. The next state is QC plus 1. So if it is 0, 0, the inputs are 0x. So you write it as 0, don't care. Then the next one is again 0, 0. 0, 0 means again 0x. The next one is also 0, 0. So the inputs are 0x. Then the next one is present state is 0, the next state is 1. So 0, 1 means it is 1x. 1x. Then here the present state is 1, the next state is 0. So 1, 0 means the inputs required are don't care and 1. So this is how we go to fill up the input for the JC, KC here. Similarly, for B flip-flop and for the A flip-flop, you can write down the input, the flip-flop input by looking at the excitation table. So that is what I have written here. For example, here it is 0 to 0, QB plus 1, 0 to 0 is 0x. Similarly, you can fill the rest of the tabular column. Next procedure is we have to find out the Boolean equation for these inputs. That is, what is the value of JA, what is the value of JB, what is the value of JC. Similarly, what is the Boolean equation for KA, KB, KC. So how to get this Boolean equation from the truth table? We know that this is possible by means of what is your Karnaugh map. So here we have 8 possible states here. So I require a 3 variable Karnaugh map to get the values of JA, KA, JB, KB, JC, KC. So after getting the values of these flip-flop inputs, I have to connect in this counter to get the desired output. After deriving the excitation table for the modified counter, we have to get the flip-flop input equations, Boolean equations for the flip-flop inputs, which is done using K-map simplification. That is the fourth step. So here we are having 6 different inputs, JC, KC for the flip-flop C, JB, KB for flip-flop B, and JA, KA for the flip-flop A. And here we are having a 3 variable function. So you have to draw 6 number of 3 variable K maps. And here I have drawn 6 number of 3 variable K maps. And here the flip-flop inputs here are, here the outputs are QC, QB, QA. And this are we know 0, 1, 0, 0, 0, 1, 1, 1 and 1, 0. Actually this indicates the inputs. You can see here for 0, 0, 0, for JC we are plotting this one. So for this sequence 0, 0, 0, 0, 0, 1, then 0, 1, 0, 0, 1, this is 3, then 1, 0, 0 is 4, 1, 0, 1 is 5, then this is 6 and this is 7. So all these 7 combinations are found in the K map. So now we have to map the input values of JC in the K map. So it is 0. This 0 is for 0, 0, 0. Then again 0. The third one is 0. That should come here. The fourth one is 1 here. Then all the other 4 are load class. So if you want, you can have this one. This is 0 and this 0 is this one. Then the next is 0 is this one. Then the next one, all the other things are don't test. Then we can also simplify the cells which are containing 1 to the K map. So if you do so here, we can combine only these 2 cells. These 2 adjacent cells can be combined. 1 and this don't care can be combined. So the Boolean equation corresponding to this combination is we have to write the variables which are common to this combination. So this row we cannot take. So if we consider this column, this is in the column QB, QA. So my JC is equal to QB and into QA, or it's an AND operation. QB and QA will give you the input value of the flip-flop JC. Similarly, we can map the value of KC from the excitation table. So from this excitation table, we have mapped this one, that is XX. All the don't gas are marked in the top row. Then after that, we have 1 R3 load gas. 1 R3 load gas. Now here all the cells are load gas except this cell. So we can combine this as a whole and the value equivalent to this is 1 as per the K-map simplification. So my KC equal to 1. Then coming to JB, the similar way you got to map this JB value. You got to map this JB values in this one and here we are getting the value equal to QA. Similarly for KB it is equal to QA and for JA it is QC bar and for KA it is equal to 1. So now I got the flip-flop input equations. All these equations I have obtained JC, KC, JB, KB, JA, KA. Then we have the next step is we have to draw the logic diagram. So this involves actually 3 number of flip-flops, 3 JK flip-flops I have drawn here. So as per our equation, first we will start with JA. JA equal to QC bar. So we go to connect the JA input of this flip-flop to QC bar. That is the first thing. This is over. Then the next one is KA equal to 1. So KA equal to 1 means it is actually high value. Any high value. VCC we have to connect. Logical high value. The next one is JB. JB equal to QA. So you connect JB to QA. So this is also over. Then KB is also equal to QA. So from QA you take a connection and give it to KB. So these 2 inputs are applied. Then JC and JC. JC is QB and QA. So you draw a AND gate here. Output of this AND gate is given to JC. The inputs for this AND gate are QB and QA. So from QA you take a connection, from QB you take another input, that is equal to JC. Then KC. KC equal to 1. So here this is actually logical 1 or high value. So this is over. The only thing left out in this diagram is a clock pulse. It is a synchronous mod 5 counter. It is a synchronous mod 5 counter. So all the flip-flops are given the clock pulse at the same time. So we have to give a clock pulse to all the flip-flops like this. You have to give a clock pulse like this. This is my clock pulse. So this is actually the diagram, the logic diagram of the synchronous counter. So this is how we go to design any synchronous counter. The first one is you go to determine the number of flip-flops required. Second one is you go to find the type of flip-flop. Third one is you go to draw the excitation table for the counter. And the fourth one is you have to simplify the flip-flop inputs using the schema. And the fifth one is you have to draw the logic diagram. Thank you.